So when we look at the results here, when we fill out the chart, we can see that the lockers that are left open are going to be the first locker. Okay, the next open locker will be the fourth locker. The next open locker will be the ninth locker. And the next open locker will be the 16th locker. Now, there are a few patterns in here, but the one that I really want you guys to recognize is that these four numbers are perfect squares. Okay, now some people may have thought, okay, well, the spacing between there is 2, 4, 6, and the next one will be 8. Okay, so if you saw that, you would be on the right track with that, and definitely that is a pattern. In fact, that is a pattern of perfect squares, that they are separated by what we call a arithmetic sequence. Okay, the gaps in between form arithmetic sequence. But these are perfect squares. So why is it that perfect squares show up in this problem? So why is it that perfect squares end up with open lockers and all the other ones are different? All the other ones are closed. Well, it has to do with the number of factors. Okay, perfect squares, because factors come in pairs. Perfect squares, when we count their factors, we can only count these two pairs as 1. So there's an odd number of factors here. Here, 1 and 2 means that since it's a factor pair, it's an even. Even with 3, there's an even number here as well. Okay, and with 4, we have an even pair here, but this gets counted as only 1. This pair is only 1, so we end up with, again, an odd. So our perfect squares give us an odd number of factors. Okay, so 5 is 1 and 5, that's even. Okay, 6 is going to be 1 and 6. Okay, it'll be 2 times 3. So 1 will hit the locker 6 once, 6 will hit locker 6, 2 will hit locker 6, 3 will hit locker 6. Okay, but that's an even number of factors. Same with these ones. Even if it's prime, it's still an even number of factors. Okay, so this is even, okay, 1 and 8. 1 times 8. This is going to be 2 times 4. Okay, that's going to be an even number of factors. With 9, we're going to have a pair here, but this pair gets counted as 1. So again, we have an odd number of factors. Okay, if it's an odd number of factors, the number of times it opens and closes is odd, which leaves it opposite of what it started at. Okay, so it started off as closed, it ends up as open. So again, same with 10. It's 1 and 10, 2 and 5. Okay, it's an even number of factors. Okay, so since we have an odd number of factors, we have the state of the door is different. So the state of the door will be different for odd and even factors. Okay, which means that perfect squares, which is an odd number of factors, ends up being open. Okay? So perfect square numbers. So if you take a look at perfect square numbers, so if you take a look at our multiplication chart, our perfect square numbers appear across this diagonal. And the reason why is they make squares. So if I look at 2, it makes an area of 2. If I look at the number, 4, it makes an area of 4. If I look at 3, it makes an area of 9. Okay, and in fact, it's a square area. So all these perfect squares end up along this diagonal. So 49 will be, 7 times 7. So we end up with a perfect square shape. Okay, so if we list them out, it's going to be 1, 4, 9, 16, 25, 36, 7 times 7, 8 times 8, 9 times 9, 10 times 10, 11 times 11, 12 times 12, and 13 times 13, and they keep on going. They get more and more spread out, but we have, these are our perfect squares, and the reason why, where they show up is along the diagonal in our multiplication chart, and it's because if we take the length and width, length of 3, width of 3, it gives us square shapes and square areas. Okay, same with like 49, it's going to give us 7 and 7, which gives us a square area of 49.